12th, everyone. 2070, most beautiful item for each query. As you can see, I've already solved this one. I'm gonna redo the solution though, I think with a new one that I think should be very efficient. You are given a 2D integer array items where items I equals price I, beauty I denotes the price and beauty of an item respectively. You are also given a zero index integer array queries. For each queries j, you want to determine the maximum beauty of an item whose price is less than or equal to queries j. If no such item exists, then the answer to this query is 0. Return an array answer of the same length as queries where answer j is the answer to the jth query. So 2 things to note here. So the problem is pretty simple. It's just find the item with the highest beauty that you can afford. And it's one of those queries problems, which is like what we had yesterday. And the thing about those problems is, or was that yesterday? I don't know. The thing about those problems is that the goal is to store some kind of information so that with each successive query, it's just easier. Well, it gets... what was it? It only gets with each successive query, you know more information. Like you deduce things so that by the end of it, it's almost like you have way less work to do because there's information that you can learn from every solution. And yeah, so let's see if I can do this because it was kind of tricky first time around. So the first thing I thought of was let's pre-process the items. If you have 2 items with the same price, you need only keep the higher beauty. If you have 1, 2, where 1 is the price and 2 is the beauty, and you have 1, 3, there's no reason for you to even worry about 1, 2. Because if you had $1, you would always spend it on the thing that has a beauty 3. So we're going to pre-process the items to eliminate those higher beauties. All right. So at first I thought the problem, one rabbit hole I went down was at first I thought the solution was to go through the items and sort them by price. And then I would binary search for each query to find the highest price that I can afford. But that's not actually the right strategy because the price doesn't necessarily mean that the beauty is going to be higher. You could have something that's $1 and it's a beauty of 1,000, and you could have something that's a beauty of 1,000 that's $1. And now every if you have 1, 2, 3, 4, 5, or like if you have 1,000, if you binary search based on price, you're gonna say, oh hey, well this one's 1,000 and I have 1,000, but it's only a beauty of 1. You should still buy that cheap one. So you see what I mean? So binary searching by price actually did do these first 3 cases just fine because those prices do correlate, but most test cases don't. What you want to do actually is search by beauty. Now we sort it by beauty, and what we're trying to do is find the highest beauty possible. Now what's not now this is a little tricky. And what it means is basically it's like you're going to search through all the beauties and find the highest beauty possible that you can afford for each query. So what we can do is we can sort the queries ascending. And then when we go through the beauties as they're increasing, we check to see if we can afford a one. And then we do one pass through and we find the most valuable item that we can afford. Now, for every successive query, we can start the search from where the last query ended, or from where the last query's result was. Because if you have you know, like 5, 5, 3, 1, 4, and 7, 5. All right. And since the queries are now sorted, you have like 1, 2, 3. So you start with 1 and you say, okay, well, this one's 3 and I can't afford it. Can I afford the next one? Yes, and that's 4. So that's cool. So let's hold on. So that's right now the best that we can do. And then the last one, 7, 5, we can't afford that. So the best thing that we can do is 1, 4. Now, since we know that everything to the left is, since everything to the left is less beauty, and since we will only increase in available prices, we can basically ignore everything to the left. So you see what I'm saying? I'm saying, so if we have 5, 3, 1, 4, 7, 5, 1 finds 1, 4, and then 2, we know that we can buy at least this, and this is the best that we can do. Everything to the left is less. It doesn't matter what the price is. The beauty is what we're looking for. So since we know that we can afford at least this one, we could just chop this off. We don't need that. Okay? So now for larger searches, with every query, as you ascend through it, you're chopping off the potential pool of answers. And so by the end of it, the search will be very small. Okay? So it is sort of O(n) squared time. In certain cases, it can be O(n) squared time, but it's actually not O(n) squared time because it's 2 values. This, it turns out to be n is the length of items, and m is the length of queries. All right, so n will be reduced every time. But let's do that. So first, we got to pre-process the items. All right, so we're going to say, the way I like to do that is by having a little price map. And we'll just have a dictionary, and since the dictionary can only have one key value, we're going to say for item in, or actually we could say for price beauty in items. We're going to say, here's a neat little line. We'll say price map price equals the maximum between either the current beauty that we're looking at or price map dot get price default value 0. So this is like a quick way of just, this is just a quick way of making a dictionary. And what we're doing is we're saying, okay, so the price correlates to the maximum of either the current beauty that we're looking at or the or the previous beauty, provided there is one. If there isn't one, then use the default value of 0. Okay. So by the end of it, I gotta stop saying By the end of it, we're just going to have a dictionary that contains all of the prices and the maximum beauties that they're associated with. So we're whittling down the array by what could be a good chunk, but even if it's not, you're only passing through it once, which doesn't really matter for the sake of time, because it's in line with the other functions. Okay. Now, we want to sort these prices by beauties so that we can go through that list of beauties. So we'll say sorted beauties equals sorted price map dot items key equals lambda xx1. So this is saying sort it, and since there's multiple values, it needs to know what to sort it by. So we'll sort it by the second value in the array. Cool. Or actually in the tuple in that case. Now we want to go through each of the queries, but remember we want to sort the queries ascending. But how do we do that while also holding on to their original index such that we could say, okay, well, let's start with the minimum query, but that's the 7th query. So that we need to associate with the 7th answer. We can enumerate it and then sort it by the values, and then those values will be tied to their original index. So tie it to enumeration and then sort it. So sorted queries equals, let's see, sorted QI, let's see if I could do this well. Sorted QI for I, Q in enumerate queries. I think that should do it, because I think sorted by default will sort it by the first value. In fact, I might just print that out just to make sure. Yes, that's right. So as you can see, the first value, so we flip them so that it sorts it by default. And so it's saying, well, okay, so 1 is the, yeah, so, well, that's not a good example because they're in order. Yeah, okay, so the second value is their index. And so let's see, the 14th value should be 151. Yep. Okay, cool. So now we can go through the queries. So now go through each query. Let's also, I've got an idea. We're going to say answer, we're going to set up that answer array. And we'll set it to 0. And we'll multiply it by m, where m is the length of queries. And that'll be useful, because this is what we're returning at the end of the day. Go through each query. If, and set the bounds of the search based after each result. So we're going to say for j, nope, for I in range, actually no, we'll say for q in, for qi in sorted queries. We're going to say, apologize, the phone was ringing. We're going to say, so we have the query. We're going to search through it. And why don't we say starting? Why don't we hold on to a value like starting point? And that's 0. Now we could say for j in range starting point up to, let's see, how about n? Actually, we want it to be sorted beauties, because items has now been whittled down a tad. So what we're going to do is we're going to say if Q, which is the query, which is the price, is less than or equal to sorted beauties dot, well, sorted beauties j, So if we can buy this one, if we can buy this item, all right, then we can set the starting point to that. Starting point now equals J. So if we can buy this item, all future searches start from at least there. And if we can buy this item, then max beauty equals, let's say max, or we could say answer I equals sorted beauties J. Sorted beauties J1. So we'll say price beauty equals sorted beauties J. And now we can say if Q is less than the price, and the answer now equals that beauty. Okay. I still am a little bit clunky with this, but I think that should do it. Nope, wrong answer. What's wrong with that? What's the matter? Oh no, if Q is greater than or equal to price. That's what it is. I'm still going to keep those breakpoints. Cool. Yeah, there we go. Pretty good time. 50. I'll take a 50, 60 any day of the week. It's good. You get the applause. And also definitely sort of a luck of the draw thing here between, you know, that could be a 70 or a 30 based on the time we run it. I'm going to just get rid of that. One last run through of how the code works. First, we pre-process the items, and we map them to a dictionary where the key is the price and the value is the maximum beauty that we've seen for that price. Then we sort that filtered out list down to, well, by the beauties so that we can go up through the beauties. And we just like the more we go through them, the higher the beauty becomes. We set up our variables for that iteration and for the answer. We sort the queries so that we increment our way through it, and so that we go ascending, so that every future search can buy at least the best one that we found for the prior search. So if I have $7, I can, at worst case scenario, I can buy what the person before me with $5 could buy. So I set that starting point, and that's where that's when the magic comes. It's like worst case scenario. We go through those queries, holding on to their original indices so that we can update that index in the array for the answer. We go through that query, and then for every one of those queries, we loop through all of the range that we're looking for. If we can buy it, then all future searches start from at least there. You can at least buy that beauty, because we know that if we go to the left, there's no need, because every successive query will be more expensive and will be less pretty. Well, and everyone to the left will be less pretty, so there's no need to even look for it. And that's it. And since the last thing is, since we initialized all the values to 0, if we can't buy it, if no such item exists, then the answer to that query is 0. So if we can't buy it, that's fine. No problem, because we just won't ever update answer I. Great problem. Thanks for sticking through it with me. Have a great day, and see you soon.